We're returning now to the concept of flow maps. This is the second lecture out of 3 on thinking about time stepping and using neural networks to help us build time stepping algorithms. What I showed you last time on flow maps was this idea that flow maps are nothing new. In fact, when we think about having a differential equation and we build something like a Runge-Kutta stepping scheme, that essentially is a flow map from time t to t plus delta t. So if I know the governing equations and the delta t is small, I have this accurate representation of the flow map. What we want to start doing is thinking about how might we use neural networks to do or to learn this flow map from t to t plus delta t, where now we can maybe even unhinge ourselves from the constraint that delta t is supposed to be small. Okay? So that's going to be today's lecture, and we're going to actually introduce a Python Jupyter Notebook to walk us through this example. So we're going to learn these neural networks directly from the data. And the advantage that you have in this neural network representation is you don't have to know the governing equations. Of course, you need a rich set of data to train this. However, if you're measuring a system in which you can see time dynamics and you do not have governing equations, the neural network will allow you to learn directly from the data. And what we'll see from this lecture, and especially the next lecture, is that we can learn different time scales and flow maps for different time scale physics by building these neural networks in clever ways. So that's what we're going to do. So here's the generic idea of a neural network, right? It is mapping an input to output. That's it. Sometimes the output is a classification of the data. Sometimes the output of the network is something else, like the future state of the data. So for instance, the input layer of a neural network here will be my solution or my measurement at time t, and I'm going to try to map that over a certain number of layers of certain sizes with certain activation functions to an output layer, which will be the solution at time t plus delta t. So that's the idea of learning a flow map. Go from t to t plus delta t, and this structure in here, you're using the full power, right, this universal representation property of the neural network to learn this mapping to a future state. So there it is. Go from time t, that's the input. The output of the network is the solution at time t plus delta t. And again, here, the delta t isn't necessarily going to have to be small for us. Although what I'm going to show you in the training that I do here is just a very standard example. In the third lecture of the series, we'll walk away from delta t being small. Right now, I would just want to make comparison between something like a Runge-Kutta stepper and learning a flow map of this sort by taking data and learning how to go from t to t plus delta t with some neural network architecture. So the system I'm going to explicitly show this on is the Lorenz 63 system. Here it is. It's a very simple 3x3 differential equation. It's got 3 parameters, sigma, rho, beta. And as you change those parameters around, you get some very interesting dynamics, including these chaotic butterfly attractors that are very famous for this system. So this is a very easy system to put into something like OD45, fourth order Runge-Kutta time stepper, right? You just march this forward into the future, and as long as delta t is small, you get a very accurate representation of the future state of the system, and in fact, you can even compute explicitly what the accuracy metrics are if you use a time stepping algorithm, because most of these come imbued with some kind of analysis about the accuracy and error and the stability of the scheme, and so we can just use that here to actually generate data for us. What we're going to try to do is move away from using something like Runge-Kutta or Euler and say, could we just learn a mapping directly from data of this system? So the idea is going to be to take a set of training data. So what you're looking at here is the training data. What I'm going to actually do, so the neural network of course, doesn't have, let's say, access to your governing equation f. What it has access to is training trajectories. So each of these balls is a different initial condition. They've been randomly picked. 100 of them. There's 100 balls there, and then I just watch the trajectories. So all these different colored trajectories here are, in fact, these 100 trajectories with different initializations, and of course they collapse down to this butterfly attractor that you see here, this strange attractor. So, and so this is going to be my training data. I run this from time 0 to time 8, and I take a delta t of 0.01. So each trajectory, right, has something like 8,000 points. And with those trajectory then, I have a bunch of data telling me how it goes from t to t plus delta t with different initializations. So I see lots of different trajectories, lots of different mappings from t to t plus delta t. And from that data, I'd like to train a neural network whose input is time t, whose output is time t plus delta t. And I want that to accurately represent what actually happens in this dynamical system. Notice the training data, when I use the neural network, it has no, like I said, it has no access to the actual governing equations. It doesn't know about the Lorenz dynamics, the Lorenz 63 model. All it sees is discrete time points and where the solution is at these different time points. And it sees how it's going from t to t plus delta t, and it's going to build a model for that based upon how I construct a neural network. So that's going to be the idea. Now I'm going to walk through a Jupyter Notebook. The Jupyter Notebook will be linked directly in the website, so you can just download that, and this Jupyter Notebook that I walk through will be available to you to play with, and you can start seeing the kind of structure that's there. So let's go to it. It's here. All right, so here's my Jupyter Notebook, and hopefully you can see most of this. You know, it's always hard to get a good color scheme with a black background that makes everything work. But here you go. You know, you just do some standard loading of, you know, NumPy is NP, bring in your matplotlib libraries and so forth, SciPy and so forth. So that's pretty standard. Now what we're going to also bring into this is we're going to bring in Keras from TensorFlow. Okay, so what the assumption is here is that you actually have TensorFlow installed and you have Keras built in as well. We're going to basically build this all out from those models. I'm actually not going to run this because it takes quite a bit of time to train, and I won't do that in real time, but I'm going to show you the results as we go through. So here is, in fact, this Keras model, various aspects of the Keras model that are directly loaded into your Jupyter Notebook so that we can access them as we run this code. So again, this Jupyter Notebook, all these files, they'll be available to you so you can look at in detail. The main thing I want to do is start building this simulator. So let's start to simulate the Lorenz system. So that's what this here is aimed at doing. We're going to produce our training data. So we're going to simulate the system, and we're going to do 100 trajectories, and that's going to be our training data that we're going to use to try to learn a neural network mapping between time t to t plus delta t. So here's our dt. It's 0.01. We run it time all the way to time 8. So we make a t vector. This is our time vector. It goes from time 0 all the way to time 8 in steps of 0.01. Okay? So that is going to be where we mark time. And what we're looking for is a mapping that takes me from some time t to time t plus delta t. So that's the flow map we're going to try to build using a neural network architecture. At first, though, the training data will be, let me assume I have the governing equations, which we do, which is the Lorenz, and then let's run those, and that's going to produce our training data. Here are the parameters that we're going to use. Beta is 8/3, sigma is 10, rho is 28. This is in the regime where we have nice dynamics in sort of this is where you get your nice butterfly attractor, and we can actually look at interesting, you know, if you want to look at how big the time vector is, here it is, print it out. And then we're going to basically start building this data in for the training. So there's two things I want to bring in here, NN input and NN output. NN input is the neural network input. So these are all the data at time t, and an output is that data advanced delta t into the future. So if I have the solution at time t, that's part of NN input. The solution at time t plus delta t is nn output. So for the first thing I'm going to do is fill these with zeros, right? So you have to pre-allocate this. So I'm going to pre-allocate the size of this thing, which is like the size of the length of the vector t, okay, and pre-populate it. And so what we're going to do is when we run the simulations here, I'm going to actually make a nice figure here. So I'm going to make a figure of all the dynamics that you're going to see in a minute. I'm going to define the Lorenz equation. I'm going to run it 100 times in a loop, and then I'm going to populate. As I take the entire time series, I'm going to start putting a solution at time t into nn input and its corresponding solution delta t later into nn output. So I come in with input-output pairs. That's what I need to train. So if I have these 100 trajectories, I have 8,000 points per trajectory, you can see I'm going to have a lot of data here to provide this thing for training, right? So something like 800,000 pairs of points are going to come in to these matrices for our use in training, right? So it's 8,000 per trajectory, 100 different realizations. That's where I got the 800,000. Okay, so here's the Lorenz, the definition of the Lorenz model. It's right there. This is just using standard Runge-Kutz solver, and here you go. I'm going to go ahead and this is the right-hand side. This prescribes the Lorenz equations, okay? And I can bring in the initial condition, the values of those parameters, sigma, beta, and rho. I bring them into here, and I run this model. So that's the right-hand side. I first define what I'm going to solve, and then what we're going to do is actually solve it right down here. First, I'm going to make some random initial data. I'm going to put in some random seed. Here it is, just some large odd number. So I'm going to make random initial conditions. They're not going to be too crazy. I'm going to say I'm going to pick some random value here, and then I, just put in some random input. Those are those blue balls I showed you. You're going to see it right here in a moment in this slide. But I'm going to make 100 different initial conditions. And then what we're going to do is right here, we're going to integrate those ODEs. There it is. NP array, integrate ODE. There it is. Lorenz with x naught j. So it's going to pull off an initial condition here, run it, and we're going to do this for all the x naughts in here. So in other words, for all of those various initial conditions that we put in, which are going to be 100, I'm going to basically run a trajectory. Okay? Now, once we've run these trajectories, right, we've got 100 trajectories we've run, we have to stack our data. And this is what we do here. I build this NN input and this NN output. So NN input is to say, all right, I've got all 100 trajectories. Let me go walk through this and say, for every single point in a trajectory, I take that point, I put it into the input, I take its next point, delta t later, and put it in part of NN output. That's what's done right here. Okay? So by doing this, what I've actually done is I've gone ahead and say, this is the solution at time t. Here's its corresponding solution, delta t later, for all 100 trajectories, for all those 8,000 points in that trajectory. So that's what I've done here. Okay? And you can just follow this through, but it basically tells you exactly how to stack that data together, and then you're set to go. This is going to give you your training data. Okay? And then we can also plot these trajectories here. So we not only plot the trajectories, but then for the initial conditions of the trajectory, we put a little ball there to see what it looks like. So again, all this code will be available to you, and here it is. This is what it looks like. This is what you get out of in your Jupyter Notebook. This actually runs very quickly. Every red dot is an initial condition, and so there's 100 trajectories here, all collapsing down, just like I showed you in the slides, right? So this is my training data. I have this, and what you're seeing, these look like nice continuous trajectories, and I have all the trajectories at every 0.01 units of time. And now what I've done is I've broken this down. So if all these are run from time 0 to time 8 with steps of 0.01, right? So you have these long trajectories that you can start building pairs of t plus delta t, t plus delta t. Okay, so that's what we're doing here. Okay, so there you go. And I think actually for each point, if it's 0.01, right? So actually, I think I have only 800 points per. I was saying 8,000. It's actually 800 training data points per trajectory. Okay. So that's my training data. And now what we're going to do is we're going to actually try to see, can we train a neural network after it's seen all this data, after it's seen all of this dynamics, can it simply learn a map from t to t plus delta t? Now you know this is a nonlinear process, right? The Lorenz equation itself is nonlinear, right? And in fact, when you think about the Runge-Kutta method you set up to run this, right, it explicitly accounts for the form of the function f, which prescribes the Lorenz model. This has no information about that. It just simply has data pairs. And what we want to do is take those data pairs and see, can it learn a representation of how to walk forward into the future? So that's what we're going to do next. This is the next part of the code, which is we're going to construct a neural network model. And the beauty of using neural networks, and in particular Keras, is it's very simple to do these things. So I'm going to call this thing deep approximation, deep approx. Okay, so this is going to be my approximation for the neural network mapping me from t to t plus delta t. In other words, the state of the system, which is three-dimensional, x, y, z at time t, to x, y, z at time t plus delta t. It's going to be a Keras model and sequential, so it's going to be some sequential set of layers. And here's how this is going to be constructed. I'm actually going to just put 3 layers in there. So I'm going to go from 3. I'm going to make the layer here. The first layer is going to be a dense layer to size 10. So it's going to go from 3 to 10. The activation functions here are going to be sigmoids. Okay? And the input dimension, of course, here that you come in with is 3. So you come in with 3, you go up to 10. That's that first layer is 10. The activation functions are sigmoid. I just made that up. I just want to show you could do sigmoid, ReLUs, linear. It turns out it doesn't even really matter which one you use, at least for this simple example. You can train it long enough and you get very nice results. But I just wanted to show you the kind of diversity of ways to specify the activation function and also ways to specify the number of layers and how big the layers are. So for instance, this first layer, again, goes up to size 10 from 3. Sigmoids is the activation function. The next layer, here it is. You add this layer here. That's the dot add. Layers dense, also has 10. Its activation is ReLU functions. Okay? So I have a sigmoid layer, which takes me to another 10, which is now going through a ReLU, which then takes me to the third layer here, which is, again, dense. But now this layer is going to take me down to 3, and this is going to be a linear activation function. Okay? So this is how this thing goes. You go up, over, down. 3 to 10, 10 to 10, 10 to 3, sigmoid, ReLU, linear. Very easy to play around with this. You can see how simple it is to code and make structure. You want more layers? Just add some more things in here. You want to go to 30 nodes in a layer? Just put 30 there. So easy to play around with this once you're in the Keras framework. Okay? So this here specifies the architecture of my neural network, my input to my output. Right? So my input comes in at size 3. My output has to come back out to size 3 as well. Right? Because I'm looking at the solution at time t. What comes out here should be the solution at time t plus delta t. Remember, my input is the solutions at time t. What it believes the output are the solutions at time t plus delta t. So it's going to take these layers and try to learn the best mapping between time t to t plus delta t. How's it going to do it? Here, deep approx, compile. So now this is going to specify for us how we're going to do this. So first of all, you can specify your loss function, MSE, mean square root error. So there are different errors you can specify, but this is a very simple one. The loss function here is just mean square root error. And the optimizer is we're going to use the atom optimizer. There's various other ones, some stochastic gradient descent, other types of optimization algorithms. We just picked these two because they're pretty standard and people use them a lot. And then once you have this, so you not only specified the architecture, you've now specified what the error metrics are and what kind of optimization you want to use. Now you can train it. So you go, deep approx, fit. So this thing here is going to actually fit this thing. And again, what is the data you're trying to fit? I'm trying to fit from NN input to NN output, and epochs here, I'm going to let it go 1,000 epochs. Okay? So you can, in fact, there's some shaded out here areas here. You can come in, you can specify, more epochs, less epochs. You can specify batch size, so many different options for how to train this thing. I wanted to keep this as simple as possible. So this thing here is going to fit this thing using these pairs of inputs to outputs. Time t to t plus delta t. Learn that map, and here is the neural network architecture that you're using. Go. So you run this. Once you execute this, this will now sit there, and in fact will run for the 1,000 epochs that I actually told it to go and do. So there is, in fact, all the results from that. And so the question is, after it's trained, how do I evaluate how good this model is? How good is this neural network model? So here's what we're going to do then. After this is trained, we've built this model. We're going to execute that model. Okay? So we're going to start executing that model, and this is what's going to happen right in here, which is we're going to use deep approx. Remember, deep approx is what I called my model, and now deep approx predict is going to take in the input, some input, and the input, remember, is a solution at time t, and map it to an output, which is the solution at t plus delta t. So this object here is my model that I learned. It is the representation of this neural network, where now I can put in the solution at time t. It's going to give me the solution at time t plus delta t. And if I want to create a trajectory, I can start off with an initial condition, put it into this model, which will walk it to delta t into the future, take the output of that, put it back in to get me to 2 delta t, put it back in to get me 3 delta t, and so forth, right? So you're just basically iterating on this model to produce a trajectory for yourself, okay? So what I'm going to do is, again, make some random initial conditions. So I specify some random seed, and what we're going to do here is run 3 trajectories. Number of trajectories, 3 here. You can run more if you like, but I just want to show it here because it gets very crowded on the screen. And so what we're going to do is we're going to do 2 things. First, we're going to run this model. We're going to take this model that we trained. We're going to take these 3 random initial conditions and run it through this dynamics. Just say, run it through the neural network. What does it do? And so here's the process of this. It's going through the loop, producing 3 trajectories that are based not upon integrating OD63 with Runge-Kutta 4.5, but based upon this mapping, this flow map that it learned. And we're going to compare that to here, where now what I do is I also take those 3 initial conditions I produced here, and I run the solution through OD4.5. And I'm going to compare them. And that's what all this plotting is down here. Here is my OD4.5 prediction. Here is my neural network prediction. And this is just making the plots nice, and here is the result of this. So this is a very simple architecture, and what you're seeing now here is 3 red balls. There's 1 right there. There's a second. There's a third. So these are 3 new initial conditions that were not in the training data. Okay, so this is my test data. And I asked the question, if I run this, how well does my model that I trained in this neural network work in relationship to just using a standard time stepper? And that's what you're seeing here. So the dotted lines and the solid lines. The solid lines are the OD4 or the numerical integration, something like Runge-Kutta, and the dotted lines are your neural network prediction. And notice, for instance, here on this trajectory, notice that these 2 just stick right next to each other. And in fact, they actually behave very similarly and eventually fall away from each other. Same thing with this one here. In fact, actually, they kind of fall away a little bit here on this big excursion. but they have very similar long-time dynamics. And the third one, which is here, actually is pretty well behaved. So what it showed you is, in fact, I'm going to show you a couple more slides here in a second, that in fact I just learned a proxy for this Runge-Kutz stepper where I knew the dynamics. All I needed to learn this was just training trajectories. Okay? So why is this important in the context of fluids, which oftentimes is what we're looking at, especially for this course in this class? It's important because in many of the models that you might have, you may have a model that doesn't accurately capture some of the physics that you're seeing, right? So there's some discrepancy between your model and you're missing some physics effects that you might not be able to coarse grain well or see in the dynamics. What this allows you to do is say, it is model free. If I can just see enough training trajectories, I will build a model for that, mapping me from t to t plus delta t, which allows you now some predictive engine. So now you could take this and do forecasting for the future state. So that's the power of these neural nets, right? It's just can learn this in a model-free way, and again, but assuming that, of course, you have enough training data. All right, so that was the code. And again, that Jupyter Notebook will be available to you. Really nice playground for you to start kicking around some code, learning how to map trajectories, learning how to build a flow map for dynamics. And by the way, just as just a highlight of another run, this is 2 initial conditions here. I just want to show you what this looks like again in a little bit more detail. Now that I have built this neural network architecture to learn the flow map, again here, 2 initial points, track the trajectories over time, and you can see the dotted and solid lines actually stay on next to each other for quite a long time. Now the Lorenz 63 is really interesting. You know that if you're off by even a little bit, then eventually you're going to diverge in trajectories, right? But notice that the attractor structure is preserved for both the neural net as well as the time stepper, even though they're going to eventually diverge from each other. In fact, here is a result of this here. So here's 2 different simulations, and what you're going to look at here is the Lorenz and the neural network. The Lorenz, let's say the true model, is the orange. This is taking Runge-Kutz steps with a very accurate solver, and the blue is the neural network. And notice in this simulation, they stay on each other for quite a ways until they eventually fall off here. This is where they diverge, which is exactly what you expect. There's sensitivity to initial conditions in this, so even if you're off by a little bit, eventually you diverge. But what's remarkable about this, at a time step of 0.01, which we trained for, these 2 stay much closer to each other than if you were take 2 different Runge-Kutz models and run it at time step 0.01. They would diverge even sooner. So it's telling you something kind of important about what this neural network architecture allows you to do. By the way, the second one, actually, they're just dead on for at least that time frame. You go further out, they'll eventually diverge as well. So this just shows you, though, the effect of how you can say, hey, I just learned a map, a flow map for some delta t from data alone, and had no idea of what the physics was. It just can take the training data, learn some nonlinear mapping from t to t plus delta t. And you saw how simple my architecture was, right? 3 layers, just put in some generic functions. And you can make that even much more sophisticated to try to improve these results. So we're going to end there with this first step in neural network training. Now notice one thing here, the delta t I picked is still relatively small. And so I've shown you how to build a neural network to map me from t to t plus delta t. But what I want to do now is walk away from the requirement of delta t being small. Can we do that? So the next lecture is going to really start to say, now that we have an architecture for training neural networks to build flow maps, can we now say, let's now back up and see if we can train this flow map to take much bigger delta t steps in the dynamics, because that's what would be really valuable to you, is to find yourself in a situation where you can build improved simulation engines because you can take delta t's that are much bigger than the constraint of something like some Runge-Kutz stepper. Thanks.